This is Cassandra Young and Mandela Scullion's 12U physics project. Mandy and I have studied the indigenous sport 1-foot high kick. With our knowledge of physics, we have found connections to the units we learned this year and the sport. We found connections to kinematics, kinetics, momentum and energy, gravitational fields, and how we could adjust the sport if it were played in micro or macro gravity. It originated from hunting parties in the north. It was historically used by hunters to signal the village once in sight that the hunt was successful. The 1-foot high kick later became a sport in the Arctic. It was usually played indoors during winter months. This sport requires explosive strength with coordination and body control. It is considered one of the most difficult and exciting of the Inuit traditional games. A way to make it easier or harder is to raise or lower the target. Kids can also play and are taught how in physical education classrooms from about grade 7 to 12. There are many schools beginning to play. For example, Bush Kids, a school based in Yellowknife, where they encourage kids to play traditional games.
As Cassandra said, in the present day, the sport is played competitively or is taught to younger kids to demonstrate strength and to test agility and body coordination. In order to play, contestants can either start from a standstill or from a running start. They must take off with both feet, yet land on the foot that made contact with the target. Falling, landing with both feet, or landing on the opposite foot will result in a failure. The target will continue to raise in increments until there is only one athlete left. 1-foot high kick has other variations. For instance, there's the Alaskan 1-foot high kick, where contestants will start sitting with one hand placed on the ground and one knee propped up. The athlete would then grab the opposite foot and attempt to propel themselves upward and hit the target with the foot that had the knee propped up. They would then attempt to land back on the foot that kicked the target without letting the foot they are grabbing drop. I'm starting us off with kinematics, a crash equation to be exact. I'm finding the time it would take for the pillow and my foot to make contact if the pillow was in motion. I set the starting velocity of the pillow to 0. I set my foot as a constant velocity of 15 meters per second and the acceleration of the pillow as 10 meters per second squared. The reason why my foot velocity is negative is because I set the forward motion for the pillow. The second equation that I did, because I didn't want to leave you with just one, is I found the distance afterwards that would have happened after the collision. And there you can see the pillow and my foot. The second kinematic equation that we're bringing to you is projectile motion. I am going to find the max height, in other words, the max height that the projectile, get off of the ground when kicking the target. Here you can find the initial velocity that I used. From there, I used SOHCAHTOA to find the vertical initial and the horizontal of the velocities. Because it's max height, we know that the final vertical velocity is going to be 0, and because we are dealing with height, we are going to be using vertical velocity. From here, we rearrange an equation that uses all of our variables in order to find the height. Now, the reason why it's negative is because we set down as positive.
For my relative motion calculations, I determined the distance my shoe traveled from when I was winding up to when it hit the target and the time it took to do so. This gave me the average velocity my shoe was traveling at the instant it hit the target, the ball. I also searched up the velocity of the wind at the time I recorded the video, which is how I got 21 kilometers per hour. With this information, I was able to determine the resultant velocity and angle the ball traveled. The resultant velocity is approximately 7.84 meters per second in the direction of north 42. We adjusted the sport a little with what we had. For my calculations, I used a tennis ball and hung it from a gazebo to use as a target for some of my calculations. However, I also used a hit-away training station, normally used for baseball, to put my target on and do some of my calculations, such as gravitational potential energy calculations. My centripetal force calculation was on the shoe that I was wearing. I used my average velocity for my relative motion calculations and measured the distance from my foot to my hip to use as the radius. I also searched up the weight of an Asics shoe size 6 women's and used it in my calculations. I then plugged in my numbers to determine the centripetal force on the shoe tied to my foot. After plugging my values into the centripetal force equation, I got a force of approximately 7.29 newtons in the direction toward. In terms of inertial and non-inertial frame of reference, think about if somebody was watching me apply centripetal force on my shoe as I kicked versus what the shoe feels as I apply centripetal force during my kick. After calculating the centripetal force, I can solve for the acceleration my shoe is experiencing during the motion. The acceleration is approximately 30.46 meters per second squared towards me. Anyone watching can see there's a centripetal force applied to the shoe as I kick. The shoe, however, is in a non-inertial frame of reference and is unaware that it is experiencing acceleration towards me. What the shoe experiences is centrifugal force, a fictitious force that will push the shoe in a direction away from me. For momentum and change in energy, when I kick the ball and my shoe flies off in the same direction as the ball, I can calculate to determine the resultant velocities after they collide. This is assuming the collision is perfectly elastic. I know that I kicked the ball and my shoe off in the direction of my house, which at the time was north 30 degrees west, so we know the resultant direction of both final velocities. I also had the masses and initial velocities of the ball and the shoe. What I needed to find was the final velocity of both objects. In a perfectly elastic collision, all momentum is conserved and kinetic energy is conserved. This is how I did my calculations and found that the final velocity of my shoe was approximately 3.25 meters per second north 30 degrees west, and the final velocity of the ball was approximately 8.49 meters per second north 30 degrees west. Another way I can tell my calculations were not far off is that one of the velocities I got when I calculated for my shoe was the original velocity I had. For celestial mechanics, I determined the change in gravitational potential energy of the ball before I kicked it and after I kicked it. I got the difference of 161,207.91 joules. The ball, however, did not escape Earth's atmosphere. This is because the vertical velocity up I kicked it with wasn't enough. I did the calculations, and in order to get the target out of the Earth's atmosphere, it would have had to been kicked with a velocity of approximately 11,181.97 meters per second up.
As I went to go kick the pillow with my bare foot, I felt a shock. Flashback to when I was taking the pillow out of the dryer, and I guess I forgot to add a dryer sheet because it seemed to have gained an electron and get a negative charge. My foot being a neutral charge coming in contact with this negative charge caused a shock since the electrons wanted to balance out so they both could be neutral. I was curious. I wanted to figure out the distance on when I first felt the shock. Average person feels a static shock from 2,000 to 4,000 volts, according to a study done by the University of Birmingham. So I decided to use an average of 3,000 volts. I have Coulomb's constant, which then using Coulomb's law, I can figure out the distance by rearranging my equation. And yeah, seems like I found the reason and how far it was to get this shock. Fun question. How would you play our sport 1 foot high kick if you were in macro or microgravity? Right now I'm going to be focusing mainly on macrogravity. This means if there's more gravity than Earth's gravity. So here's our guy, here's our target. What I was thinking is mainly with electric fields. You'd have to use conductive metals for this, since they're able to freely hold and give and take electrons. It would be the only way. Now, you have two parallel plates. In order for a charge to actually happen, something along shoes, because you need to jump and kick, or a suit, that can also contain a charge. Since it's macrogravity, we want something that'll go upwards. If we assume this is positive, then we want something that would go the other way, as in a negatively charged shoe. Now, the equation that would be set up is we need the equation for the force of the electron would be Fe is equal to the charge epsilon, Q being the charge of the shoes.
the force of gravity is equal to mass times acceleration due to gravity. We need these to be equal in order for this to actually work. So that's how we get charge epsilon is equal to mass times acceleration due to gravity. But we need the electric field strength, so we can rearrange to isolate for epsilon. Now, let's assume that it's 3 times the mass of the Earth's gravity. I am 52 kilograms, and let's assume that that's me in there. Here, and our shoes have a charge of 0.01 coulombs. Here, we can set up our equation like this, and in order for me to play on a planet with this amount of gravity, I would need the electric field to have a charge of 1.5 times 10 to the 5 volts per meter, with shoes that have a charge of 0.01 coulombs. Just like macrogravity, we're going to be using the same equation. However, this time, unlike macrogravity, it'll more or less essentially be the same thing, assuming we have the same charge on the shoes. Because microgravity has a weaker strength of gravity than the Earth, meaning that it's a lot easier to, well, I don't want to say a lot easier to escape the field, but a lot easier to escape the field. You aren't as attached to the Earth's surface, or the planet's surface. So instead of wanting to go farther out, you're wanting to more stabilize. So instead of using just a regular G for gravity, we want to have a desired gravity, which is the Earth's gravity. So using my weight and the same charge for the shoes, we're going to use our desired gravity instead to find the strength of the field, which is 5.1 times 10 to the 4 volts per meter. Well, that's the end of the video. This is Mandela Scullion and Cassandra Young doing 1 foot high kick. It is currently 5:41 a.m. The sun has risen. And I am very tired. So, I hope that this video was a little to your liking. And yeah. Please give us a good mark, Doc. Okay, thanks. Bye. Woo!